Good morning. Welcome to Krishna's classroom. Our next consideration is constructing a class of simple functions, or what are known as simple functions, and approximate a given measurable function through these simple functions. Okay, the strategy is this. If these simple functions pointwise converge to the measurable function, then of course they have to be measurable. Then see that the integration of the measurable function can be defined as a limit of the integral of these simple functions. Now that is going to be the strategy to define integral. But before all that, let us not bother about it right now, but we will come to that. Okay, let us first define what simple functions are. A complex value yes it's a measurable space XM to C said to be simple if its range finitely many points. That means for such functions, the range consists of finitely many points. That means you have S is a map from X to C and the range of consists of complex numbers alpha 1, alpha 2, alpha n for some n. The important point is that there are only finitely many values in the range. Okay. Now we shall see what kind of function is it. Now we define by AI. Okay. We shall non-negative simple functions. So that's what we want to work on. That means all these alpha 1, alpha 2, etc., alpha n are assumed to be greater than or equal to 0. So let be the distinct values so let AI designate the set of all x belonging to x such that Sx equal to alpha I. We have assumed that alpha i's are all non-negative. Okay. Then S is equal to sigma chi AI. Now you can easily verify that this satisfies all these requirements. That means on AI, so what you have is this. You have now X coming out. If this alpha 1, alpha 2, alpha are distinct, then you see that A1 union AN, AI is M for I not equal to J. On A1 it takes the value alpha 1, on A2 it takes the value alpha 2, etc. On AN it takes the value alpha n. Now you see that chi AI takes the value, see, chi component. That is a characteristic function of AI. Now what you have done is a linear combination of these characteristic functions, and you can easily check that S, if x belongs to AI, Sx equal to alpha I with S defined in this. Okay. Now we say that, see, if AIs are measurable, then chi AI is measurable. So AIs are measurable functions. Conversely, if S is measurable, then each AI is measurable. Conversely, if S is measurable, then S inverse of alpha I thus we have S is measurable if and only if so this is the criteria for the measurability of S. Okay, so that defines what are called the measurable functions. Now what you have is, see, for example, if you take for example, let us draw the graph of, let us take a real value. Okay, consider the interval. Yeah, one of the remarks I want to make, AI could be any measurable subset of for instance, if X is equal to the interval AB, AI need not be an interval. In fact, let us take the function, let us define Sx equal to A1 so the set of rationals in complement. Then S takes and equal to now you see that means you are at the rational points in on the interval AB, the function takes the value A1. At the rational points, it takes the value. That's the meaning of that. Okay. Now both the rational points form a a subset of the interval AB, which is measurable. So also the set of irrational points. Therefore, this is a something more general than a usual step function. In the step functions, because you recall when we were defining Riemann integration, okay, our technique of approximating involved approximating the function on the interval AB through what are called step functions, because we were subdividing the domain into subintervals and then working on it. Okay. So the sets that you had were, say, if it is A1, A2, etc., AN, these sets A1, A2, AN were all intervals whose union is the whole interval. In that case, again we were approximating with a simple function in the new language, which was also called a step function. That means on each AI, on each interval AI, it was taking a value small ai. Okay, so that is the nature of the function. So in the graph itself, it looked like a step function. Now this is a generalization. We are no more insisting now that the AIs should be intervals. I mean, it could be weird sets like Q intersection X or Q complement intersection. Okay, so that's just a remark. Now what we want to do is construct an approximation of a measurable function using simple functions. That is our task. So we have the following theorem. Take a non-negative function. I mean, there is a reason for taking considering only non-negative functions at this stage. Whereas a simple function need not be, in general, a non-negative function. So we consider we shall consider non-negative measurable. Which means we consider functions f from x to infinity included, because we consider extended real valued functions. That means fx is and we are also assuming that these functions are measurable functions. Now we have the following here. Let's take the statement of In this theorem, what we assert is that we can construct a sequence of measurable simple functions which is monotonic and approximates to f from below. Okay, so let be measurable. Then there exists simple measurable functions such that first condition is and all these are bounded by Sn point-wise converges to infinity. Now, I should also remark here that since we are considering f to be extended real value, non-negative, f could take on some set the value plus infinity. But Sn's take only finite values. So you see that this inequality is satisfied at every point. Further, Snx in that case, what you call diverges to plus infinity, because this is a monotonically increasing sequence which diverges to plus infinity for x belonging to those sets where f takes the value 2. So this is the central theorem that we are going to work. So we start with the measurable function f. Then what we assert is that there exist simple measurable functions Sn on x such that these two inequalities are satisfied. So let me just broadly tell you how we construct these functions. I mean, maybe a little bit of before we express them through expressions, we have a feeling for what exactly. Let us try or take a specific situation and then try to work. Now let us take, for instance, delta n to be to the power minus. So that we start with delta 1 by 2. Now what we do is, let us take a non-negative real valued function with x taken as the, for our pictorial clarity, we will take x to be the real line. Okay. Now we take, you see, this is from 0 to infinity. So the range consists of 0 to infinity, infinity included. This is the range. Now if you plot the graph, it will look something like this. May not be continuous. I am just taking a particular example, or even allowing it to take the value infinity at some point, and then some. Okay. We also take this function to 0 at some points. So this is the graph of it. Now what we do is the following: 0 to 1, okay, and we define the following. Okay, we split this into the range into 3 sets. So we take 0 infinity to be written as half to 1 union 1 to infinity. Okay, this is for the case delta 1 equal to, which is equal to half. So I break this up into, see, this is delta 1 half. So I have the range split into 0 to half, and then half to 1, and 1 to infinity. Right? Now I'll define S1 as follows. Okay. Before that, cross some lines here. Okay. Now consider the set where it is less than half. The function takes the value less than half. Okay. And then consider the set where the function takes the value. So this is less than. This is the portion where it takes. Now consider the set where it takes the value from half to 1. What is that? That I'll mark. So this is the set over which the function takes the value, or the function takes the value between half and 1, and rest of the place, you see, the function takes the value. So rest of the place, the function takes the value greater than or equal to 1. So we split it into 3 sets. Now let us define A1 to be equal to F inverse of, that means the set of all x that's the set A1. Let me define A2 as F inverse of half to 1, which is equal to the set of all x belonging to R, for which and then A3 as we shall fix the notation later. But let us first understand this, what this is. This is equal to the set of all x belonging to R, for which 1 less than or equal to, therefore infinity. So these are the three sets that we consider. Now we fabricate the function S1. So let us write down S1 as the lowest value of this interval is 0 times the characteristic function of A1 plus half times the characteristic function of A2 plus 1 times the characteristic function of A3. So what is it? On this set, this is A1. This is your A1. On this set, we take Sx to be equal to 0. Now on this set, this is A2. On the set A2, we take the function to be this one, half. Okay. And on the rest of the place, we take the function to be equal to, that means A3, the function to be equal to 1. So we are now, our given function is now replaced by the following function. Okay, this is a step function. This is the step function that we are working with. This is your S1. Okay. So on A1, we take it as 0. On A2, you take it as half. On A3, you take it as 1. So that it's a bounded function. So if f is measurable, then A1, A2, A3 are measurable. Okay. Therefore, S1 is measurable. Is a simple function, simple measurable function. and which is bounded. S1 is bounded by 1. So what you get is this. S1 takes 3 different values, namely 0, half and 1. Is bounded and takes values 0, 1. These are the 3 values it takes. Okay, now let us go to the construction of S2. How do we make S2? So let me, once again, I may not be the same figure that I draw, but try to get you some idea of what it is. Here it takes the value. Okay, so S2 let me construct. For S2, what I do is, I have 1, 2. Okay. Now let me refine the subdivision. What I do is, so n equal to 2. Let me take the mesh point for the subdivision. Delta 2 equal to 2 to the power 2 to the power minus 2. 1 by 4. So what I do is, I write infinity as 1 by 4 to 1 by 2, 1 by 2 to 3 by 4, intervals of length 1 by 4, 3 by 4 to 1, 1 to 5 by 4, 5 by 4 to 6 by 4, 6 by 4, that is 2, which is 8 by 4, union 2, So in the second stage, we have gone up to the interval 2 and we have divided this into 8 equal parts. You have okay. And we look at the portion where the function maps to 0 to 1 by 4. What is that? See, this is the portion that gets mapped to 0 to 1 by 4. Then we take 1 by 4 to 2 by 4, that is half. We map this. So you see that this function is this. So this is the portion. This is the region where the function gets mapped into the interval 1 by 4 to 1 by and so on. So this is 1. So you see that if you take any specific interval, you can find out it's pulled back and then call that the corresponding. So you have got these intervals or the sets marked on R, which gets mapped into a certain region. Okay. Now these sets, so we will designate this by. So what you have. So we take now we'll make the notation. Now for the time you look at only this. This is no more the same A1 there. But I will designate it properly later. On which I set the function to A2 1 by 4 to sorry F inverse of by 4, on which I set this equal to 0, and then I take F inverse of 1 by 4 to 1 by 2, and on this I set the function to be 1 by 4 and so on. Now suppose I take the interval, so A1, A2, A3, A4, A5, A6. So let me write A6 equal to, just giving an example, F inverse of 5 by 4 5 by 4 to 6 by 4, where I set the function to be A7, A8 and A9. So the function S2 takes values between 0 and 2. Which are the values? 1/4, half, 3/4, 1, 5/4, 6/4, 7/4, 8/4 is 2. Okay, 4/4 to 5/4, that is 1 to 5/4, and then you have 5/4 to 6/4, and so on, and takes the value 1 here, 5/4 here, 6/4 here, 7/4 here, and 2 here. So these are the values that the function is. And you see that AIs are simple. Sorry, AIs are measurable. And SX plus chi, what is it? 0 times chi 1 plus chi 9. Okay, this is S2. This is your S2. Now S2 is a measurable function. So we have constructed S1 and we have constructed S2 now. Both are measurable functions. Now one thing that you observe immediately is that S1 less than or equal to S2. Okay. So in this way, we start constructing S3, S4 and so on. In S3, what do? You will be taking the interval from 0 to 3 and partitioning. And how do you partition it? Partition it with, with interval length given as delta 3, and delta 3 is by definition 2 to the power minus 3, which is equal to 1/8. Okay, so it's a further refinement of the partition, right? But we advance a bit and go up to 3. Or in other words, we are going to subdivide each of these intervals again into 2 subintervals. That's what we are happening. So we have started with this, divided these intervals into 2 subintervals. Again, each one of them we are going to subdivide into 2 subintervals of equal length, and so on. With for S3, the mesh length is, or the length of the interval is taken as 1/8. Okay. Now you see that you know the construction, the rule of construction. Now you can write down this easily, and you get delta now S3 is bounded by 3. S1 is bounded by 1, S2 is bounded by 2, and S3 is bounded by 3. And we continue this process. Okay? And we continue this process. Now it is clear how it is coming. I will write down the formula eventually. You can check. Just the same. Okay. If we continue this process, we'll get a sequence of simple functions which are measurable and bounded. So what we end up with will be 0 less than or equal. Eventually, you see that each one of this Si is bounded by the given function f. Okay, each one of these functions is bounded by f. Sn is bounded by n. Okay, Sn is bounded by n. Now you see that each one of these is bounded by f. So we get the first step. So the process is, first in the range, take the interval 0 to 1, divide it into 0 to half, half to 1 and 1 to infinity. That is in the first stage. The second stage, you divide each of these intervals by half, to half of their intervals. So you get 4 intervals from 0 to 1, another 4 intervals from 0 to 2, because we push it up to the limit as 2 here, or the bound as 2. So you get altogether 8 intervals, sub-intervals between 0 and 2. And then we proceed the same way, we get S2 constructed. Now you get S1 less than or equal to S2. S1 and S2 are both measurable functions because f is a measurable function. Okay. Now you go to S3. S3 is bounded by 3. And then you have the interval, sub-interval length as 1 by 8. So it will be split into how many? 8, 8, 8. So 24 intervals between 0 to 3 and one huge interval. Okay. So it's actually there will be 25 intervals. Okay. And then once again, in the same way, you can construct the function S3 and so on. What can you say about Sn? Sn is bounded by n. Bounded by Sn is bounded by n. And how many intervals are there? You see, what is the mesh length? The mesh length is 2 to the power minus n. So each interval 0 to 1 of unit length will be divided into equal 2 to the power n intervals. And how many such intervals are there? Up to n, it is going to be n times 2 to the power n sub-intervals. And then of course the final interval 0 to, what is that? From n to infinity. Okay, so you get n times 2 to the power n intervals and plus 1. So altogether Sn will be defined on n 2 to the power n plus 1 sub-intervals. Each sub-interval of this part will be of length 2 to the power minus n. Okay. So the interval length here is going to be or minus on for this part, and this of course n to infinity. Okay, right? And then you can define the corresponding SL, right? So let us define this SL. Now let me use the now we define what happens is in the definition of SN 0 to n is given as the union of k equal to 0 to n to the power n minus 1. Okay, k divided by 2 to the power n, k plus 1, and that is the breakup of 0 to n. You can easily see that total number of intervals correspond to the value of k ranging from 0 to n 2 to the power n minus 1. So there are n 2 to the power n intervals of length 2 to the power minus 1. And the upper bound is going to be n. So what you get is this 0 to infinity, we split it as 0 to n plus union okay. So let me now try to write some notation. We'll write a k n to be equal to f inverse of the power n. Okay, where k of course ranges between 0 to n 2 to the power n minus 1. Okay, and then we write an to be f inverse of infinity. That's the final definition of this. Okay, so that I can check whether we have got it right by putting different values. Now on AKN, take S x equal to the lower value, that is k by 2 to the power n. Now this for k equal to 0, 1, etc. running up to n 2 to the power n minus 1. Okay. So how many sets are there? There are n into 2 to the power n sets are there, akn. And on each akn, we take Sx to be equal to this, right? And on an, which is equal to Snx to be equal to, that's the definition. So we have now Sn defined as follows. Snx is equal to k by 2 to the power n, or k running from 0 to, and then of course all this is for right? So we define, so let us now formally write akn. I define as f inverse of for k ranging from 0 to etc. n to the power n minus 1, and all this for this is the collection akn. Okay. Now you fix n, you get the Sn defined, and we write an to be equal to f inverse of n to e for n equal to, so what we obtain is a sequence of functions. Sequence of functions are, and what you do is Sn equal to k by 2 to the power n on a. Okay. Equal to n on a. Here a ranges from 0, 1, n to the power n minus 1, and this is a. N is defined. So this is the definition of Sn. Now you see that Sn is So these sequence of functions Sn are now measurable functions. Now what more we have to verify? We have to verify that at some x, the sequence Sn x converges to x. Okay. Now next what we do is so we have completed the construction of these what are called simple functions. Next we claim the following. I have tried to bring some clarity to the definition of Sn than what is done in say Runian. It's the same function that is constructed. Now our claim is this. Now slight abuse of notation where x takes the value infinity, you get Sn x would be the sequence 1, 2, 3, etc. going to infinity. Okay. At and what you have is you have a sequence 1, 2, 1, 2, etc. diverging to this is what happens at those points. So that is easily settled because if x belong to x is such that infinity, then and that is so which is equal to f of x. Now we have to consider the case where Sn x is finite. Now suppose f is bounded. Fx it's an arbitrarily chosen point where fx takes a finite. Then there exists a n such that fx is less than or equal to n. Point. Then you take as the smallest integer for which this happens. Then what happens? Then you see that what is going to be Snx? What you see that fx lies between okay. Now we take, now you see that take scales or let me use the number n. Now you see that equal to n equal to n. What I want to say is Snx is bounded between so you see that S1x is going to be 1 take n to be for n and beyond that what happens? Beyond that, see, this is the first S1 is defined up to this 1, S2 is defined up to this. This is n, so Sn is defined this value. Okay. And when n is greater than n, okay, if fx is less than n, then you see that Sn fx happens to be, suppose you take, so it is in what happens? N plus 1x lies between n and n plus 1. In fact, what happens is, if fx is bounded by n, that's what we are doing. Then you see that fx is which implies S belongs to n and in fact, for every greater than, this one, that is the x for which this takes this value. That's what we are doing. So what happens is that this is in fact fx is squeezed between some restrictions of this kind, k by to the power n, and what happens is that if fx, suppose this is the value of x, now you see you are going to have fx lying between fx belonging to an interval to the power minus n for every n. Okay, what does it mean? As n tends to infinity, the interval collapses to the single point f of. That means, what does it mean? Means which implies f of x, because we are working on a fixed x. Okay, as or the sequence converges to f of x. So whenever fx is not infinity, you see that it gets successively squeezed in intervals of length 2 to the power minus n, and as n becomes large, you see that this interval would collapse to, the interval length would collapse to 0, which in turn means that this interval collapses to the point fx. Therefore, you see that Snx tends to f of x as n tends to constructed a bounded measurable simple functions Sn such that this means that this also includes this statement also includes the place where f becomes infinite and the corresponding sequence Sn becomes 1, 2, 3, etc. The value Sn takes at those points would become 1, 2, 3, etc. which will go. Okay, so that completes the proof. We are going to use this extensively. This construction, particular construction is not required in your future arguments. But all this says is that there exists a bounded sequence of monotonically increasing simple functions which approximates the function f from monotonic increasing or non-decreasing. What I mean to say, monotonically non-decreasing, measurable simple functions and approximates f from below, that is SNX So that's the conclusion. So we have completed the proof of our theorem. You see that in this portion what we are doing is, as once Snx, if n, capital N is the bound, is the or fx is squeezed between n and n plus 1, then you are going to have beyond the value capital N, Sn is going to be a sequence, and at each, for each value of n, you see that fx is trapped between in intervals of length 2 to the power minus n, so that as n tends to infinity, these intervals squeeze to 0, which means they converge to a point, or they what you call, or reduce to a single point f of x, which in turn tells you that at x, Snx converges to x. That's the argument. So thank you very much. Let me conclude this.